All right, here we go. Linear systems of equations. Example 4, a two-variable equation where both variables are to the first power would indeed create a line, and that's the case on both of these. So the visual again would be two lines, and the solution to the system would be that ordered pair that solves both equations, which visually is that point of intersection. So we've discussed that, and that would be the deal there. So we're looking for that point of intersection, and then the question in my mind becomes, should we use substitution or elimination? I hope you recall from a previous example that when you have the variables lined up, elimination makes sense. On the other hand, looking at it from the other point of view, substitution requires that a variable be by itself. And even though we could isolate a variable, one of these variables, I still would suggest to you that elimination would make more sense. So, elimination. Elimination. Okay, sorry to waste your time. But anyway, yes, elimination makes sense here. All right, now, should we get rid of x or y? It doesn't matter, it's a coin flip. All right, so let's flip a coin here. Sorry. This is embarrassing. I need to bum if I could, a coin. You have one for me. Okay, good. All right, here. I'll come get it from you. All right. Oh, thank you. All right, this time you gave me a dime? Wow, that's awesome. Okay, so let's do what we did before. Heads is x, tails is y. All right, boom. Heads is x, tails is y. And it is this time heads. All right. So x. Let's focus on x. And if you recall, we want to find the lowest common multiple for 5 and 3. What's the smallest number that 5 and 3 both go into? 15. You guys are good with that. All right, so we're going to build both of these up to 15. Actually, we want 15x and negative 15x, so they'll eliminate, right? Elimination! So, how about a 3 on this one? Remember, the goal is to generate a 15x. So if we distribute 3 on both sides of that top equation, we will get 15x plus 27y, make sure we distribute it to every term, and then on the other side we have negative 75. Make sure you multiply it all the way through on both sides. In algebra, you're doing the same thing to both sides of an equation. This new equation is algebraically equivalent to the other one. All right, if that became positive 15x, don't we want this to be negative 15x? We already got the negative. How about you multiply it by 5? Again, on both sides. So we have negative 15x negative 15x plus 10y equals 75. And if we add the like terms in the two equations together, see the like terms were lined up. That's kind of a tip-off that you want to do elimination. So x goes away, and this is now 37y. 27y plus 10y is 37y. And then that's 0. Okay, so 37y equals 0. And there's a y there, so you divide by 37. Don't let the fact that that equals 0 bug you. Just keep solving. So y equals 0. So the y-coordinate of that point where those two lines cross is 0. That's just a general picture of the question. Okay, so y is 0. Let's go find x. Stick 0 into one of those equations. I don't think it matters which one. I hope you would agree. So if we put 0 into this equation right here, we would have negative 3x plus 2 times 0 equals 15. I'm just going back to this original bottom one. And 2 times 0 disappears basically. So negative 3x equals 15. And divide the negative 3, solve for x. And x turns out to equal negative 5. And you come over there and put that in there. And there it is. All right. Good job, everybody. high five, every high 10, whatever. Oh, yay, oh, high elbow, right? We're supposed to elbow now, all right? Give each other an elbow. Good job, everybody. That would have been example 4. We'll do 2 more of these. And again, the typical occurrence is that we get one ordered pair when we solve a system, although there are 2 other things that could occur, which we'll see in the next 2 examples. I can't wait. Are you excited? Me too.